Hello, my name is Carl Cook, and I'm President and Chief Technical Officer of IntelliDynamics, a division of Biocomp Systems. And today I would like to show you how to do clustering with self-organizing maps in the NGO. And first off, self-organizing maps is not a clustering technology, although most people look at it as being so. If you were to ask Mr. Cahonen, the man responsible for inventing the algorithms, he would be the first guy to tell you that it's not a clustering technology. Self-organizing maps are a mechanism by which you can take large dimensional data and cast it down onto a two-dimensional grid. But in that grid, with a little bit of calculation magic, you can know the distances between various objects that are cast on that grid and actually create dividing lines between groups of objects based on their similarities and differences, which is basically clustering. So what I am going to show you is the SOM window in the NGO. And this looks very similar to the regressive modeling window. There's a few fundamental differences, which we will go through. So I am going to bring in a file called animals_sm. And SM stands for small. Not that the animals are small, it's just that the file is very small. It only has 12 rows. And so by bringing that in, it automatically loaded it, and I have something called label, which is what the animal is, and presuming that insects are animals, and then some various attributes about them, whether they have arms, legs, wings, teeth, fins, whether or not they're hairy in size. And some of this is a bit of a judgment call on my part. I'm just trying to create a data file that we can use as an example to demonstrate this. But there's only 12 rows, which also shows you how to do things with a small data set. Now, we don't need to do any pre-processing with this data whatsoever. We'll just use it as it is. And the self-organizing map technology will try to group these various entities based on the similarities and differences of their attributes. So we will go to the SOM construction window straight away. And what we have over here are the labels being a tag. That is, it's an identifier that's not going to be used by the model, which is the first column in the file, which is the way that it should be. And also then all the inputs are mandatory. And because if you have the NGO switch them on and off, then it'll tend to reduce the data models smaller and smaller, because then with fewer inputs, the object distances based on their similarities and differences become smaller, and eventually it will just try to throw away all the inputs, which we don't want. Although there may be some opportunities there later that we can explore. Also, since this data file is only 12 records, splitting it into modeling, optimization, and selection data sets is not very effective. So I'm going to make this 100% for modeling and 0 for optimization and 0 for selection. Yes, you can do that. And also, I'm not going to hold any back from the process. And so we will not regress, we will cluster or group based on similarities and differences these records, 12 records, entirely using the modeling data set. And the next part of it is how to set up the models. Now when you got how many dimensions do we have here? 1, 2, 3, 4, 5, 6, 7. We're going to take 7-dimensional space and cast it onto a 2-dimensional grid. There's a little bit of art as to what the dimensions of this grid should be. And if you make it too small, if you made it say a 2 by 2, it doesn't work very well. You're trying to pack things down into too small a space. And if you put that 200 by 200, well, we've only got 12 records, so they're going to be separated substantially from each other. So there's a little bit of art in this. And so let's just look at a 10 by 10. And that'll give it some space to operate in, and it's not too big. 10 by 10. Not too big and not too small. And all we have to do is push the go button. And now we get this 2D representation where the red are hot areas. This is called a heat map. The red are hot areas where there's high concentration of certain types of records, and the green is empty space. It's kind of got large distances between the red areas, which are closely related objects. And it looks like kind of like a Star Trek display. So if your boss comes by, you can start this up and run it, and it'll look very impressive. We'll let this run a little bit. You don't have to let it finish. It's done 75 out of the 100 models so far. We're getting close to finished. What it's doing is trying alternative models to try to find the ones that will separate the attributes of these records the best way. And even Toivo Kohonen, the inventor of the algorithm, says that since there are some random initiation of weights involved, that doing a search is the best way to construct SOM models. So now we go over to the maps list. And here we have our various 10 maps that we created. And we can right click on this grid over here, and we can select various different metrics: overall distance between objects and the distance between modeling records. And we can sort that. And in this case, smaller is better. So here we have a map that has the smallest distance. And we can see here that the apes and the human and the cats, those are kind of mammals, are over here. Here's butterfly and robin over here. And then here's trout, salmon, porpoise, whale, shark over here. And so they're kind of distant from each other. Now if we slide this slider, what it will do is it will start drawing distance-based boundaries. In other words, start grouping things together. And we can cluster that. We got 5 clusters. I want to get something. Here's a little bit more art. I want to get a little higher. That's 6 clusters. I can start pulling these things together. And here we got 5 clusters. And 5. Okay, now we've got 3 clusters. So, okay. So now we've grouped the apes, the humans, and the cats. Those are kind of the mammals together. And the butterfly and the robin are in the same kind of gray space. And the shark, whale, porpoise, salmon, and trout are all in the same kind of gray space. And we don't see all the records because if they fall in the same bin here, each square, then it only shows one of them. It doesn't show the entire list for that bin, especially if you're working with large data sets. Now what do? We've kind of clustered this. Now we can go here and export to clusters. And I'm going to call this clusters and mals. I've exported out a file. And let's see what that file is telling us. It says that cluster 1, so we have cluster ID and then the attributes. So ape, dog, cat, and human are in cluster 1. Okay, that makes sense. Trout, salmon, porpoise, whale, shark are in cluster 2. Okay, that makes sense. And the robin, bee, and butterfly, those are things that all have legs and wings, are grouped together in cluster 3. And intuitively, to you and I, that seems to make sense. Then you can use this file to to whatever way makes sense for you. You can sort them by cluster or whatever. If these were customers, they may be customers who are most similar to each other in terms of their attributes or behavior metrics or whatever you're using for data. And you can then treat those clusters of people appropriately in terms of marketing campaigns to generate leads or sales strategies to approach the customer with certain kinds of opportunities and values and those types of things. So anyway, this is just a quick introduction on how to mechanically use the clustering capability that has underlying technology called self-organizing maps to be able to do that. And if you have any questions, shoot me an email at cmcook@intellidynamics.net, and I'll be happy to answer any questions you might have, or leave a comment at the below this video. Thank you very much for your time.